Good morning. This is the Software Skills Lab, and today we will be talking about advanced examples regarding key values and cache eviction policies. As you know, this is the last module that we will be working together. During the first module, we looked at caching and hash tables. During the second module, we looked at one-hop distributed hash tables. And during last week module, we looked a bit more into cache eviction policies, and either in the case of local hash tables, in the case of distributed hash tables. So today we will be talking about something more practical, as I've announced last week. This lecture will be maybe a bit shorter than last times, because then we will be working a bit more together to try to see in practice how these systems work. So in particular, we will be using Redis, which is a system that is used in production across plenty of systems, and it's used as a key value store, and we know that by now there are strong similarities between key value stores and caches. So what is Redis? So Redis is known to be a lightweight key value store. Lightweight in the sense that it consumes little resources. It's very easy to start. It's light in terms of CPU resources, memory resources, and it supports many systems. It is an in-memory key value store. It means that all the keys and values, all the entries in the system are stored only on a volatile memory. So the RAM part basically of your system. And although it does support persistence on non-volatile devices, this is supported via some configuration parameters. We are not going to look into this, but it's somehow easy to use if you need that in future. Nevertheless, we will be only looking at in the in-memory case, because of its similarities with the systems that we have been looking at so far. The values that can be stored in the key value. So remember, we are dealing with the key value. These values can be complex data structures. So far, remember, we've been looking at integers or maybe values. So now we are dealing with something a bit more complex, such as strings, lists, maybe even hash maps. So if you want, in the hash map table, you would have a key that identifies something, let's say sport, and then here you would have a hash map, which is once again a key and a value, a set of key and values, in fact. You might have sets as entries of your key value. You can have also sorted sets. So the values that are used as, so the set that is used as a value of your key value is itself being sorted natively by the system. And this would allow, for instance, to implement efficiently range queries, meaning to efficiently answer queries that asks, tell me if there are keys, such as their value is between a value A and a value B. If the type of the value, what we store here, is for instance a sorted set, then this becomes very efficiently implemented internally by the key value store. Interestingly, Redis also supports replication. We have seen briefly the replication feature in key value stores. Or if you remember, we were looking at possible optimizations so that a given key and its values can be replicated across the system, across the network, because of some optimization strategies. In this case, Redis implements replication mainly mainly to handle fault tolerance. If there is a node that fails, you always want to have at least a number of copies of that key value pair available to answer correctly queries. And finally, as a last element of introduction to Redis, it has we will see later that it has a lot of cache eviction policies supported, and by default it supports the least listened reused strategy, which by now we know how it works. So one easy way to understand better how Redis works is to actually use it in practice. So in this next few slides, we will use an online service, try.redis.io, which runs a Redis instance, a Redis program for you, and that you can use basically live to see quickly how it works, understand the syntax, and we do this via a command line interface that this website offers. So if you open this website, you can first basically follow these steps and try the tutorial first. In this example, I follow the tutorial myself, and you will see that we are basically setting and putting, or setting, which means putting a key and getting its value. In this case, this full string is the key. This is our key. And instead, the value is this Jupyter. Which means that if this operation completes correctly, then once you issue get for the same key, you have to get Jupyter here, and this will work. You can also try out other commands, the sets, to set a given value, to increment atomically the value of the given key. This would become 101. And I strongly encourage you to follow the tutorial, which it is nicely done. And there is a bunch of pages of this tutorial that you can follow. You can issue the command next in this Redis command line, and just follow the instructions. It's super easy, and it gives you a nice introduction, a very gentle introduction to Redis. So one useful feature of Redis is that it allows you to set time to live of keys, and it tells you after how long a given key should expire. In this case, basically, we are setting a time to live of the key users to 120 seconds. So in the previous example, we were setting a given value for this key. Then we say that we want this key to expire after 120 seconds. So if you do this in the command line, and then you actually wait, you wait on your clock for this amount of time, you will see first how much time it is left for that key, and you will see that this value decreases in time. If you do this after a few seconds, you will see that this increase. There are a couple of corner cases that also are explained in the tutorial. Is that at some point you might get a value of -1 as a TTL, or -2. In the case of -1, it means the key will never expire. The key basically stays forever. In the case of that -2, it basically the key does not exist anymore. not. So these are two special corner cases for the value that is returned by the command ttl. One interesting feature of Redis is that, once again, the values that we use in our key value, these values here can not only be primitive types, as we have seen so far, basically for integers, simple, so some kind of values, strings, so, but also, more interestingly, these can be more complex data structures as lists. So in this case, we show what is the syntax to configure and add entries to a value whose type is a list, and we do this by using the command rpush. And we see that we are adding basically 3 elements to the list. We are adding this at the end of the list, and you will see easily that there are 3 different elements, and this operation has a constant time complexity. There are a couple of, let's say, complementary operations that you can do on those lists or those complex values. For instance, you can check how many elements are currently stored, the length of the list if you want. You can also add elements not at the end of the list but at the beginning. I'll push. So if you want, this is right push and this is left push. And you can also check all the other details in terms of complexity of the operations and possible other corner cases by issuing the command help rpush or help rpush. If you have the values that are lists, you can easily extract subsequences of those elements from the list using the lrange operator. The first parameter is the name of the list that you want to use as an input, and then basically you have the index of the first element, in this case 1, and the index of the last element that you want to retrieve. There are, once again, as the tutorial explains, there are a bunch of corner cases for which that the value of the second parameter could be -2, for which or -1 or -n. This basically says what is the last element to use as the counting from the last in the list to extract from this list. As you see, the complexity of this operation is linear, with n being the length of the range, in this case 7. What does it mean to have those informations regarding the complexity? Is that if you have long ranges or ranges with a bigger covering more elements, these basically will take more time, let's say in some workloads, to execute. We can add elements into a list, we can also remove them. This would be the two commands that we can use, lpop or rpop, so left and right, removing elements from this list. These are very efficient operations which are implemented in a constant time, you see here. I didn't specify so far, but these operations are all basically providing atomicity guarantees. It means that if there are multiple threads or multiple queries being issued to remove elements from those lists, then the system guarantees that there are no what we call race conditions between those threads, that they are not left with, in an incoherent state, and that basically the system remains somehow usable and it behaves in a somehow expected manner. So now we look at another possible data structure that you can use as values in your key value store, and these are sets. It basically means a set is a data structure that prevents duplicates in a given collection. You cannot have, which is not the case for lists, for instance. So here you would have a unique set of items with distinct values in each entry, K1 and K2. So what is the syntax here? It's quite simple. We can have insertions into a set. We specify the name of the set to use, and then we have some values. We'll add another one. Here we create another set has a different name. We also add an item. We can, of course, remove elements from a given set, or check if a given key is a member of the set. If a given value is a member of the set. And these operations are also quite efficient. It is also possible to efficiently combine two different sets. This is the first one. This was the other one. Here we are combining them, doing a union operation, which is the typical one that you do on sets. And this instead has a complexity of O with n, where n is the number of elements in the first set plus the second set. So the sets are somehow handy, but the problem is that they are unsorted and they do not work so super well for a number of problems. So now we see how this can be solved by using sorted sets. The syntax is very similar to what we had before. Now instead of s add, we have z add. We also specify the name of the set to use. And then what we do, we basically use a kind of let's say a score or a metric that is used to sort those entries. In this case is year of birth, and then here we see how we add another entry for another programmer basically, and this parameter is used to keep those elements sorted inside the sorted set. And the complexity to do those operations, meaning the complexity to insert and to keep that sorted set sorted, is logarithmic in the number of elements sorted. This has a number of advantages, such as, for instance, range operations can now be done in a very efficient manner, and as you see, the complexity now depends not only on the number of let's say not only the size of the range, but also the number of elements in the set, and this still is super efficient. The last possibility that we see here as a possible complex data structure that you can use as value in a key value store with Redis are hashes. What is a hash is basically a map between string fields and string values. So this is now everything is a string if you want. And you can do this if you think about Java programming or object-oriented programming more in general. Basically, you can use this approach to implement or represent, more simply represent in your key value full objects. And let's see how this works. Here we are creating a new key value of type whose values are hashes. This is the name of the collection we want to use. This is, if you want, the first entry, and then we start adding fields. So we have a string field for the key and a string value for the value, and you do this for all these entries. So here you can basically model name here, email, whatever else you want to do. And then by using this approach, you can now do search operations or a bunch of other possible mutators or operations that are going to increment those values in a very efficient manner. In particular, here you can get all the fields that are associated with this key in a time that is linear to the number of the fields of that object. So far you've been using Redis directly from that tutorial. If you want, the instantiation and the deployment of that Redis instance is completely transparent to you. It's been deployed somewhere on the web, and then look, now you're using it via some web interface that is probably issuing GET and POST requests via some HTTP protocol, which is by coincidence what we were trying to do during the first 3 projects. But now we are going to see a bit more, let's say, in practical terms, how to do this ourselves, how to deploy a Redis instance. In particular, we are going to use Redis as a cache, which is the ultimate goal of this part of this last module. Redis has a support to automatically evict old data and to add new data. And so this is basically what the cache or caches are supposed to do, and it is exactly the same behavior as other popular real-world programs or caches. One of them is, for instance, memcached, which you might have heard before. If you remember, what we tried to do during the previous project was to set a given amount of keys, k, as the maximum number of keys or entries that were allowed. In the real world, here we are not dealing anymore with the let's say discrete entities or a number of entries in the key value, but rather we set the amount of memory that the cache is allowed, and then this has a direct consequence on the number of entries there. So basically, by tuning that parameter, we are supposed to observe side effects on the efficiency, on the response time, on the cache miss and on the cache hits that Redis reports. At the time of this presentation, when we looked again at the latest versions, Redis has support for at least 6 different cache eviction policies. One of them is obviously somehow dumb, which is no eviction, so it never evicts. And then otherwise, it supports a few more, which we are now going to look a bit more into detail. So if we go through the list of the supported eviction policies, once again, the no eviction is somehow dumb, because of course there would be issues when you reach that memory limit that you have set. Of course, this can be solved by having a super large and increasingly bigger memory, but this doesn't scale, basically. The next cache eviction policies is called all keys LRU, and what it does is that when this limit is reached, the Redis decides to remove the less recently used keys first from the cache. The next variant is somehow similar. So it also it's called volatile LRU. And what it does is to also remove the less recently used. But the variant is that it only does this eviction on keys that are about to, are going to expire. What are the keys that are going to expire? Those for which there is a TTL, a time to live, that was set, and for which the time to live is not anymore 0. The next example is quite straightforward. It's a random policy. It just remove one at random, as we have done also on our simpler implementation. The volatile random is somehow mirrors the previous case. It also removes keys at random, but only among those that are going to expire. Once again, those with the time to live. And then the next one, it's called volatile TTL. And what it does is as follows. First, it looks at the keys that are going to expire. And then it removes those with the shortest TTL. So those with the shortest TTL are the keys that are going to expire next. So now the question is, which is the best policy? And the answer is there is no one best eviction policy that fits all use cases. And this is why you have to choose and to adapt the key eviction policy according to the workload that you are going to face. And interestingly, you can imagine that the workload, in general, in the real world, the workloads are somehow dynamic and they actually change during time. So a given eviction policy that works for some time, then maybe it becomes less effective and you might want to change it while the system is running. How you decide which one to use, or how to decide whether the system is behaving in a good or a bad manner. Redis reports some statistics, for instance, in terms of cache misses. And you can, if you do that, you can look at the entries regarding key space hits and key space misses. And of course, you might do this periodically, let's say as a maintainer of a cache system, and you can monitor those values. And you might see that maybe you have too many or too few hits, and you might want to decide to change the key eviction policy to have a better, more performant system. And as I said before, there is a nice feature in Redis is that you can actually change the eviction policy at runtime, and this can be done directly via the Redis command line, which is what we are going to use also during the practical part. One interesting detail about the Redis least recently used cache eviction policy is that it's not an exact implementation. What it means is that instead of actually taking the key that is actually the last recently one, it does sample some keys. And then among those, it picks the least recently used. They do this for actually a good reason. It's a very practical reason. And there are more details explained here in this website. Is that usually doing LRU costs itself memory. So this needs to be spared. And by having this approach, you can have a more balanced entries in the keys, in the keys and in the cache. And basically, by having implementing this approach, you can observe on realistic, on even synthetic benchmarks that the latencies and the cache miss and hits are all improving. There are more details on that website. I encourage you to take a look. It's quite an interesting and nicely written piece of technical blog. So highly encouraged to read this. Now, a short summary of what we will try to do during the practical part. We are going to use a real Redis instance deployed on your machine. We will use an open source benchmark, memtire benchmark. There are instructions, so we will try to follow them together for all major distributions. And then the idea is to use Redis according to 3 different eviction policies. So we need to use to see how to change eviction policy, and then to run some benchmark against that configured instance, and we can try to discuss the results. To actually run Redis itself, there are a bunch of options. One is using a Docker container. So take a look at here. There are instructions. There are instructions that explain how to do. You can also use your operating system package manager. In particular, for Linux and macOS, there are several options, several packages that allow you to install Redis very quickly, very easily. I haven't tested this on Windows, and I'm not sure that this is going to work. And perhaps the Redis itself might work, but whether the memtire benchmark works on Windows or not, I have no idea. So you're strongly encouraged to use either Linux or Mac. If this is not possible, let me know, and I will try to allocate a temporary server instance for you on our cluster. So this concludes this shorter than the other presentation, because the theory part is basically what we have already covered during the previous modules. Now we will join all together we will join the WebEx session, and we will try to follow and to run some real benchmark for Redis. There is a PDF document that gives some more details about a possible approach and possible list of tasks that you might want to try to better play with Redis.